Ever find yourself noticing patterns, like everywhere? Maybe tiles on a floor or, I don't know, music?
Oh, absolutely. Humans are pattern-seeking machines, aren't we?
Totally. And today, we're diving into a really specific mathematical kind of pattern. We're using the amazing online encyclopedia of integer sequences, the OEIS.
A fantastic resource.
Isn't it? We're focusing on one entry, 00000020.
Right. A 000208. It sounds maybe a bit dry, the number of even sequences with period 2 ends, but there's some really neat stuff packed in there.
That's the plan. We want to unpack what these even sequences with period 2n actually are. What's the even part mean? What's period 2n? And, why count them?
Exactly. The OEIS entry itself is our guide here. It gives us definitions, examples, formulas, the works.
So let's start with the basics. What kind of sequences are we talking about?
Okay, so first off, these are binary sequences, just zeros and ones. Think like computer code at its most fundamental.
Zeros and ones. Got it. And the period 2n part.
That means the sequence repeats itself after a certain length, and that length is always twice some integer n. So if n is, say, 3, the period is 2 times 3, which is 6.
Okay, so a block of 6 digits made of zeros and ones, that just repeats over and over, like 0, 1, 1, 0, 1, 0, and 0.
Precisely. That block of 2 10 elements is the fundamental period.
All right, now the crucial part, what makes one of these sequences even? It's not like the number 4 is even, right?
Yay. No, not quite like that. It's about the contents of one period. An even sequence is one where within that single repeating block of 2 can elements, there's an even number of ones.
So if even number of ones, 0.
Okay. And because the total length of the period, 2 can, is always an even number. Well, if you have an even number of ones, you have to have an even number of zeros, too.
Ah, okay. So it's balanced in terms of parity. Even ones, even zeros. Like if the period was 4, so n2, then 1100 works. 2 ones, 2 zeros.
Exactly. That's an even sequence.
But something like 1000 wouldn't be because it has 1, 1, and 3 zeros. Odd counts.
Correct. That fails the even test.
Now, there's another layer here mentioned in the OEIS, this idea of equivalence. Sequences being the same if you can translate them or swap the ones and twos.
Yes. This is key to understanding what A0002 or 8 actually counts. We're not counting every single sequence that fits the criteria.
Right. So what does translation mean here?
Think of it like a cyclical shift. Imagine your sequence is written in a circle. If you have 00011, shifting it one step gives 1001. Shift again, 1100, again, 010, one more, and you're back to 00011.
Ah, like rotating a necklace pattern.
Exactly. All those rotations, those translations, are considered the same fundamental sequence for the purpose of this count. They represent the same underlying pattern, just starting at a different point in the cycle.
Okay, that makes sense. And the other rule, exchanging ones and oozes.
That's sometimes called complementation or bit flipping. You take your sequence, say 0011 again, and swap every 0 for a 1 and every 1 for a 0.
So 0011 becomes 1100.
Precisely. And under these rules, 00, and 1100 are also considered equivalent. They are, in a sense, mirror images of each other.
So we're counting the truly unique patterns after we group together all the ones that are just shifts or bit flips of each other.
That's the core idea. It reduces the number of things we need to count significantly.
This sounds like a good time for that example the OEIS gives for N2.
Perfect timing. So if n22, the period is 2 times 2, which is 4.
Okay, period 4. How many possible binary sequences of length 4 are there?
2 to the power of 4.16.
Yep, 16 total. The OEIS lists them all out from 0000 all the way to 1111.
Right, so first step, which of those 16 are even? Meaning have an even number of ones and therefore 0 zeros.
Okay, let's see. 0000 is even, so that counts.
Okay.
Then we have the ones with 2 ones, 0011, 01010, 1001, 900, then 10, 1100.
6 of those.
And finally, 1111 has 4 ones. 4 is even.
So 1 plus 6 plus 1 is 8 sequences initially seem to fit the even criteria. Wait, the example said 7. Did I miss something? Good catch. Let me recheck the OEIS example description. Okay, the OEIS itself lists the representatives after equivalence, but it implies starting with the even ones. Let's list the even ones again carefully. 0001, 0011, 01201, 0101, 1001, 1010, 1100, 2 ones, 001s. That is 8 total even sequences of length 4.
Okay, 8 initially. Now apply those equivalence rules.
Right. So take 0011. Its translations are 1001, 0111. So those four are all one group.
Got it, one group down.
What about the bit flip of 0011? It's 1100, which is already in that group. So that rule doesn't add anything new for this specific group.
Okay, what's left from our list of 8? We used up 0011, 1001, 1100, 010,
We still have 000001LN test 1111.
What about 0101? Translate it.
Shift 0101 once, you get several 1. Shift again, you get 0101 and 01. Form another group of 2.
2 more accounted for. And the bit flip of 0101 is 0 and 10, which is already in its group.
Correct. So that's group 2. What's left?
Just 00011 and 1111.
Okay, 0000. Shift it. You just get 0000. Bit flip. You get 1111.
Ah, so 00000 and our equivalent under the bit flip rule. They form the third group.
Exactly. So our initial 8 even sequences boil down to just 3 distinct equivalence classes. We can pick representatives like 00000 and 0101.
3. And that's why the sequence entry says A23. That makes perfect sense now. It counts the unique types of patterns.
Precisely.
So what are the actual numbers in this sequence? A000020. How does this count grow as n increases?
The OEIS lists the first few terms, 1, 1, 3, 4, 12, 28, 94, 298. It grows pretty fast.
Wow, yeah. 1, 1, 3. We just figured out the 3. What about the first 2 ones?
Well, the OEIS tells us the offset is 003. That means the sequence starts at index n0.
Yes, but the period is 2 times 0, which is 0. What does that even mean?
It's a bit of a degenerate case, you could say. An empty sequence, perhaps. The convention yields one unique even sequence for n0. Then for n1, the period is 2.
Period 2, the sequences are 0, 0, 0, 1, 10.
Right, which are even.
On 11.
Are they equipped?
Shift 0000, lip 00011. Yes, they are equivalent, so only one unique type.
And that's why A11 form.
Okay, 113. Then it jumps to 4 for NL3, period 6, then 12 for NL4, period 8. It definitely ramps up.
It does. And the OEIS, helpfully, provides formulas to calculate these terms, often relating them to other sequences in the database.
Right, I saw those. They looked a bit dense, involving A00000003 and A00000013.
Yeah, they link A00000013N and A00000000A. If n is odd, it's just half of A00000132.
And similar formulas involving A000010.
Exactly. It shows this beautiful interconnectedness within the OEIS. We don't need to deep dive into what A00000013 or A000016 count right now.
Probably wise.
But just know they likely count related types of binary sequences, maybe without the even constraint or using different equivalence rules.
So our sequence, A000008, is like a specific refinement built upon those potentially more general counts.
That's a great way to put it. The formulas leverage the counts from those other sequences to arrive at the specific count for our even sequences under these particular symmetry rules.
It's like mathematical Lego, building specific structures from standard blocks.
Kinda.
The entry also mentions some references, like Sloane's books, a handbook of integer sequences, and the encyclopedia of integer sequences.
Those are like the Bibles for sequence enthusiasts, essential references.
And a paper by Gilbert and Riordan on symmetry types of periodic sequences. Sounds like it goes deeper into the math behind those equivalence rules we discussed.
Definitely suggests a more formal treatment of the symmetries involved.
And then there are cross-references to other sequences like A00000003 we already mentioned, and A00000006. It really is a web.
It is. And finally, those keywords. Non, easy, nice.
Non is not negative integers, right? Makes sense, we're counting things.
Yep. Nice. Probably implies it has some elegant mathematical properties. Easy. Often.
Easy for whom? Maybe easy compared to some really obscure sequences.
Perhaps. Or maybe easy to compute using those formulas, even if understanding the derivation is harder. It's relative, I suppose.
Okay, so let's try to wrap this up. What's the main thing to remember about A000208?
I'd say it's the count of unique binary patterns that repeat every 2n steps, are balanced, even zeros, even ones, and where uniqueness is defined by ignoring starting position shifts in 0 to 1 flips.
And that N2 example, going from 16 possibilities down to 8 even ones, and finally down to just 3 unique types, 00000, 000101, really shows how those equivalence rules work.
Exactly. It crystallizes the concept.
So thinking beyond just the sequence itself, where might this kind of thing pop up? Why is it interesting to count these specific patterns?
That's the really cool question to ponder, isn't it? You could imagine applications anywhere. Periodic binary signals with certain balance properties are needed. maybe in digital communications. Error-correcting codes sometimes rely on balanced blocks.
Or maybe signal processing looking for specific repeating waveforms.
Possibly. Or even theoretical computer science, studying the complexity of patterns. The study of sequences under symmetry operations is pretty fundamental in combinatorics and group theory, too. It tells us about structure.
So it touches on quite a few areas. It really makes you appreciate the OEIS as more than just a list of numbers. It's a map of mathematical connections.
Absolutely, and a starting point for exploration.
Well, if your curiosity is sparked, definitely head over to oeis.org, look up A000028, check out those related sequences, maybe even peek at the references. Who knows what connections you might discover?
It's a fascinating corner of mathematics, full of surprising depth hidden in simple-looking sequences of numbers.